This is the Section 3 podcast for Chapter 6, and this section essentially is a statement of Newton's second law. Newton's second law states the acceleration produced by a net force on an object is directly proportional to the magnitude of the net force, is in the same direction as the net force, and is inversely proportional to the mass of the object. We're going to simplify that into a mathematical equation, and here it is. Here's your equation. You have acceleration here. The acceleration is directly proportional to the amount of net force, so that's in the numerator of the equation, and it's indirectly proportional to the mass of the object that you're trying to move. And if we use units such as newtons for force, kilograms for mass, and meters per second squared for acceleration, we're going to get this equation. Acceleration equals net force over mass, and we'll simplify it by writing it like this. You're going to see it like that a lot. Now, Newton, in this picture you're going to see it written slightly different. Force equals mass times acceleration, and that's done by changing it's awful. Let's use the pen. A is equal to force divided by mass, and if we multiply both sides by mass, we end up with force is equal to mass times acceleration. So you can write it like that also, and this is the way it's written here in this book, on Newton's in this picture of Newton standing on Galileo's shoulders, of course. So if you remember one thing from this chapter, remember this. Newton's second law, acceleration equals force divided by mass, or force equals mass divided by acceleration. So let's look at what directly proportional and indirectly proportional mean. This is a good picture right here. Directly proportional means if one goes up, the other goes up along with it, and he's representing that by the two thumbs going up. Inversely proportional means if one goes up, the other goes down, and that's represented by one thumb up and one thumb down. So if the net force on an object is doubled, then its acceleration is going to be doubled. That's directly proportional. If the mass is doubled, then the acceleration would be halved. That's inversely proportional. And if both the net force and the masses are doubled, then the acceleration is going to be unchanged. And we can show that real quickly here. Let's take acceleration is equal to force divided by mass, and if we double the force and double the mass, you can see these two terms essentially cancel out, and we're still left with the acceleration being unchanged. So let's do a little math. The car can accelerate at 2 meters per second. What acceleration can it have attained if it is towing another car of equal mass? Well, if you use the same force on twice the mass, you're going to have half the acceleration. So the correct answer would be 1 meter per second squared. So if 2 meters per second squared is equal to whatever the force is divided by whatever this mass is here, and if we double the mass here, then it's going to have this here. So we're left once again with 1 meter per second squared. A car has a mass of 1,000 kilograms. What is the acceleration produced by a force of 2,000 newtons? Well, if you plug it all in here, you're going to see that you plug in the force of 2,000 newtons here, the mass of 100,000 kilograms there. Do the math out, we end up with 2 meters per second squared. Now this is interesting right here. I wrote newtons as kilograms times meters per second squared. That's another way of writing newtons. And if you look at that, here is a unit right here of mass. Here's a unit of acceleration. And another equation for force is mass times acceleration. So that all makes sense. If the force is 4,000 newtons, what is the acceleration? If we take that same 1,000 kilogram car and we double the force, essentially going from 2,000 to 4,000, then you're going to simply double the acceleration. So how much force or thrust must a 30,000 kilogram jet plane develop to achieve an acceleration? Now here we don't have the we don't know the force in this case, so it's a slightly different equation. In this case, we would use the other form of force equals mass times acceleration and plug in mass, the acceleration, and we end up with 45,000 newtons. So you've seen the equation used two different ways. Once when you don't know the acceleration, and now when you don't know the force. So what is the relationship among an object's mass and object acceleration and net force on an object? It's Newton's second law. The acceleration produced by net force on an object is directly proportional to the magnitude of the net force, is in the same direction as the net force, and is inversely proportional to the mass of the object.